Hello and welcome back. We are discussing the final section from Chapter 4, Additional Applications, Exponential Models. We're going to tackle actually this second learning objective first, examine applications involving exponential models. Okay, so one researcher's model suggests that inoculating X people to a virus follows this model. I of X equals some constant times 0.90 to the X minus some other constant. And this is in thousands of individuals, and that's how many people will get infected if we inoculate X people. Okay, so if there are 5,000 susceptible people, we're supposed to be able to figure out what constants A and B might be. And then we'll follow that up with how many individuals get infected according to this model when you inoculate 2,000. Okay, so 5,000 susceptible individuals actually gives us two useful pieces of information. One is maybe the obvious one. If you inoculate 0 people, then 5,000, since our units are in thousands, inoculate 0 people, there's our input, then 5,000 of them could be get infected eventually. So susceptible implies that they could. Okay, so, but there's actually another point that this implies too. It means that if we inoculated everyone, that is 5,000 was our inputted number of people, so x equals 5, then there would be no infected people. So this, again, assuming that the inoculation is perfectly effective, which may not be totally accurate, but this is our simplistic model. So that actually gives us two pieces of information to set up equations here. So the first one says that I of 0 would have 0 for the input and 5 as the output. And then plugging in 5 for the input, we could get 0 for the output. So although each of these equations has two unknown constants in it, they both contain A and B, we've actually got enough information to nail down what these ought to be because we've got two distinct equations. Okay, so maybe one strategy is to take the first equation, once simplified, and solve it for one of the variables. Let's say solve it for A. It doesn't actually matter, but so we take this first equation and rewrite it just by adding B to the other side. Okay, then we can replace A with 5 plus B in this other equation. That looks something like that. Now, the advantage to that is this equation down at the bottom here has only one constant in it now. It's only got b's in it. So with some expansion and simplification, this is taking away 2.95 something from both sides, combining these two terms. 0.59b minus 1b is actually negative 0.4 something, and then divide off that constant and we get a value for this. So b is something like 7.21. Then we can go back to either one of our original equations that has a in it and use that to figure out the value of the constant a. So if we dump in 7.21 for b, add that to both sides, we get that a is right around 12.21. So we've accomplished our goal. We figured out the actual model that we had set out to figure. So now we know this is our inoculation model, and in part B we follow this up with an actual computation involved. So the target level, target may be the wrong word, but the value we're supposed to look for is 2,000 individuals. I'm sure given most diseases are not especially great, we don't want 2,000 people to get sick, but that's what we're looking at. So that translates to solving I of x equals 2. We got to be careful. This is not asking for x to be equal to 2. X is the number of people that we inoculate, so this is actually an output they're giving us. Okay, but since we've got this formula for how many people get sick, then we can take this entire expression and set it equal to 2. Okay, then typical algebra stuff. Add 7.21 to both sides, that gives us our numerator. Divide off 12.21, gets us our denominator. And then we're faced with this classic kind of equation that addition, subtraction, multiplication, division, none of those typical strategies get us out of. We need to have x in the exponent, so a logarithm is what would help us out with that. So if we take a logarithm on both sides, natural log for instance, we're going to get to use that nice property of logs that lets us bring this exponent down. It's not quite as tidy as natural log of e to the x. These don't cancel each other out perfectly, but it's enough that it gets that variable out of the top. So there's the equation rewritten with x out in front. Last thing to do is divide by natural log of 0.9. That'll give us an approximate 2.6, etc. I'm going out to 3 decimal places because x is in thousands of individuals. Probably don't need to go farther than 3 decimals because this is a whole number of people now. So the claim is remember x is how many people get inoculated. So this is saying if we inoculate 2,676 people, then only 2,000 of folks will get sick. So this last sentence is kind of interesting with respect to this model. It suggests that if we inoculate 2,600 people, then there's going to be an additional 300 and some that don't get sick. So remember, there are 5,000 people total. This is claiming that only 2,000 of them are going to get sick, and the other 2,676 are the ones getting inoculated. So there's some number of people, more than 0, 300 and what is that, 24, who aren't inoculated but also aren't getting sick. So this is actually a really interesting model in life science that basically is claiming that inoculating people saves other individuals from getting sick, which is kind of cool. So another example, but we're going to make use of the same function. So we'll steal our hard work from example 1, reuse this inoculation function, and now our task is to apply marginal analysis to estimate the change in number of infected people when we move from 1,000 inoculated people to 1,010. So in other words, what's the effect of inoculating those extra 10 people? How does that change our number of infected people? Okay, so marginal analysis is this derivative, using the derivative to predict this change. So we have a nice formula for this, our new output, and just to remind you of all these pieces, so this is a guesstimate for our new output. This is the actual value that we're starting at, and then the rest of this equation is an estimate of the change. Actually true, maybe I'll write that. So this piece, the piece based on the derivative, this is the estimated change in output. So it's not necessarily the actual value, because the derivative is only using the slope at this point to make a prediction, but it's our best guess without actually plugging in for 1,010 to figure out what the change in this output might be. So in this case, remember that x is in thousands, so the actual input, 1,010 people, is an x value of 1.010. So that's the input we're trying to estimate here. And what we're going to base that off of is the starting point of 1,000. So moving from 1,000 to 1,010, that's what indicates that 1 is the starting point and 1.01 is where we're headed. We're still using the derivative at this starting point, and then this is the change in value. The difference between 1,000 and 1,010 is 0.01 thousand people. Okay, so let's just start figuring out these pieces. So I of 1 is what we get when we go back to our inoculation function and dump in 1 for all the x's. That gets us something like 3.779. Again, we're going out to 1,000, so we get a whole number of people, 3,777 people. We also need to figure out I prime of 1, so that's going to involve taking the derivative of our function. So remember, much like e to the x, some constant times 0.9 to the x basically just survives as it is. Exponential functions are already so much about their own change that their derivative just isn't that much different from the actual function. The only other catch is that we get this extra constant, the natural log of the base of this piece. That doesn't occur when we have e to the x. Or it does, but it's just that natural log of e is times by 1, so it doesn't actually affect the answer at all. And then we're supposed to take that derivative and plug in x equals 1 to get some approximate value. So doing that, it tells us the slope is negative 1.1578. Again, a whole number of people, we'd be looking at negative 1.158. So the prediction here is that if we increased by 1,000 inoculated people, we'd be dropping the infection by 1,158 people. Again, that same idea that infecting some number of people actually prevents that many people and a few more from getting infected. And then now that we've got all the pieces, let's estimate. So remember, the things we needed to figure out were I of 1 and I prime of 1. We just did those. So plugging in I of 1, we got our 3.779. Taking the derivative, we got negative 1.1578. And getting a computation, there's our prediction. So The estimated number of infected is, again, moving back to thousands, or regular people from thousands, 3,767 using marginal analysis. So the estimated change, if you note, between these two values is what? 7 people. So if we inoculate 10, then we're only adding on to that 7 additional. Sorry, we're dropping by 12 total people, the difference between these values. So the 10 people who got inoculated, and then 2 additional folks who were sort of saved by contact with inoculated individuals as opposed to infected ones. That's it for this video. We'll be back in the next one for more with 4.4.